So, so moment of inertia, we have two important formulas here. One is called theorem of perpendicular axis, perpendicular axis. It says it says that this is only valid for a laminar body, for laminar bodies. If I say laminar body means two-dimensional bodies, like you can use it in a ring, you can use it in disc, or you can use in a rectangular plate or a square plate, rectangular or square sheet or a square plate. In these figures, you can use this theorem, that is theorem of perpendicular axis. And it says that if you have any body, any sheet that you have kept in some plane, xy plane, let's suppose, and any point, if I say this is x-axis, and let's suppose this I'll take as z-axis, and along x-axis we have moment of inertia ix about x-axis, and about z-axis I have moment of inertia iz. Then the third axis, which is the perpendicular to the plane, that is iy, will be given as the sum of ix and iz. Here, one thing you remember, that body is kept in yz plane. YZ plane. If you keep the body at xy plane, now let's suppose the body is kept like this. This I'll write as x, and this is y. Then you need to find the third axis. Now the third axis will be z axis. Third axis will be z axis. So iz you can find now by adding those two moment of inertia in which it is kept, like x and y is kept. So ix plus iy will be iz. That means this formula we use when the body is in xy plane. Body is in xy. Similarly, if the body is kept in yz plane, you can use ix is equals to iy plus iz. This formula we can use when it is in body is in yz. You understand, Neil?
Yes, sir.
Okay. Body is in yz. Now, now, if second theorem that we are going to discuss is called theorem of parallel axis. Theorem of parallel axis. Theorem of parallel axis says that now this is more important because it's valid for all type of bodies. Valid for all type of bodies. All type of bodies. 1D, 2D, 3D. Okay. And what is it all about? It says that if you have any arbitrary shaped body like this, and you want to find moment of inertia about a given axis, this, let's suppose about this axis I am trying to find the moment of inertia. What you should do, Try to find where is its moment of inertia, where is its center of mass. So say इसका center of mass जो है वो यहाँ पे है. Let's suppose this is the center of mass. Center of mass वो place है जहाँ पे आप लिख सकते हो इसका पूरा mass m. Now next step is सेंटर ऑफ मास से होता हुआ एक ऐसा लाइन ड्रॉ करो, एक ऐसा एक्सिस ड्रॉ करो जो गिवन एक्सिस के पैरेलल हो. गिवन एक्सिस हमारा ऐसा है तो हम एक लाइन ऐसे ड्रॉ करेंगे. इसके अबाउट मोमेंट ऑफ इनर्शिया हमें मालूम होना चाहिए. वी शुड नो व्हाट इज द मोमेंट ऑफ इनर्शिया. लेट्स राइट दैट ICM. And you should also know the distance between the two axes that we write as r, small r. Then you can find this moment of inertia very easily. What you should do first, you take the moment of inertia about that axis which is passing through center of mass plus m into this is r square. This is called theorem of parallel axis. Understood, Neil?
Yes, sir. Yes.
Now let's try to use use this theorem to find moment of inertia for a continuous body. Continuous body. Continuous body like a ring, disc, sphere, cylinder. You cannot find the moment of inertia by just mr square because it is not in a single m, the system of particles. So you have to first try to find, you have to take a very small element, that mass you can take as dm, try to find its moment of inertia, and then you should integrate it with the proper limit to find the moment of inertia of the complete body. So this is the concept that you are using here. If I say moment of inertia of a uniform rod, moment of inertia of a uniform rod. So moment of inertia of a uniform rod, if I take, let's suppose this is a uniform rod and I have to find the moment of inertia. Axis should be very much defined. So first I am taking the axis, about an axis, about an axis, passing through about an axis, that is passing through center of mass and perpendicular to the rod, perpendicular to the rod. So let's suppose this is the axis here, this is center of mass, will be the midpoint only here, let's suppose, and this is the hand. This is the axis. What this total mass you can take as m, and the complete distance of the rod, length of the rod, you can write as l. So I'll take a small element here. Let's take a small element, and this I am taking at a distance x from the axis, and its length is dx. The small element length is dx. Up to here, understood?
Yes, sir.
Now dm can be found as the mass density, as is rod. So rod mass density is always mass by length multiplied by small length dx. dm equal to m by l dx. Now try to find the moment of inertia of this part. Is di equals a point mass only. So point mass moment of inertia is mass into distance squared. Distance is x. dm I can write as m by l, that is constant only, and here is x. So, no, this is into only, it's not x. So x square dx, integration of x square dx. Now for the limit part, you can see this distance is L by 2 on the left side, and this distance is L by 2 right side. Left side we take as negative distance, right side we take as positive distance. So the limit of integration should be negative L by 2 plus L by. So this is M by L. X square you can write as x cube divided by 3. And the limit is minus L by 2 plus L by. That is M by L. Now L by 2 cube will be L by 8. L by 8 into 3, it will be L cube by 24. And here is minus, so this will be minus L cube by 24. Minus minus will be plus. So it will be M by L. This, if you add this L cube by 24 plus L cube by 24, it becomes L cube by 12. One L you can cancel. So what we get, the moment of inertia of the rod that we are getting is basically ML square by 12. Understood, Neil?
Yes, sir. Just 1 second, I'm copying it down.
Yeah, yeah. Copy.
Yes, sir, done.
Okay. Now let's take, it is about an axis. Uh, Passing through one ends of the rod. It's not center of mass. Passing through an end of the rod. And perpendicular to its length. Perpendicular to its length. So if you have this rod, then here in any axis that is not passing through center of mass, always try to use parallel axis theorem. Any axis which is not passing through center of mass and you have to find the moment of inertia, use parallel axis theorem. For that, first you should know where is center of mass. Then draw a axis that is parallel to the given axis. You can see this is the given axis here. This mass complete is M, and this here you can distance will be L by 2. Now, this about this axis, I know the center of my moment of inertia. Just I have calculated. It is ml square by 12, and this I we have to find. So what I'll do, Neil, that I'll use parallel axis theorem that says that first write what is the moment of inertia about ICM, and then you take total mass and whatever is the distance between these two axes that you take. So here you can see it is ml square by 12, and this is m, and r I can take as l by 2 square. So it is basically ml square by 12 plus this will be ml square by 4. If you add these two, then you are getting ml square by 3. That means the moment of inertia about any axis that is passing through one end of the rod, that you can write as ml square by 3. Understood, Neil?
Yes, sir. Understood.
Now in your target book that you have, Akash, just go to page number 41. You have that book right now?
Yes, sir. I have. I have.
Yeah. Please go to page number 41.
Yes, sir.
You see, try yourself question number 46. Can you see that?
Yes, sir. Yes.
So here you see it is a rod. It's a rod here. It's a uniform rod, and they have to find the moment of inertia about the given axis. Axis is CD. About an axis CD. Okay. AB or CD, moment of inertia about an axis CD. CD is here. This is CD. And L by 2 AB is the center of mass. This is the center of mass. Okay. Rod is right long here. Okay. This is L by 2. This is L by 2. And this is given as L by 4. So if this is the center of mass, then I know moment of inertia about this will be always ICM will be ml square by 12. ml square by 12. And about this I have to find. So I'll use again the parallel axis theorem that says that I is equal to ICM plus capital M into R square. ICM formula we all know about that axis is always ml square by 12. And here R, the distance between two axes is given L by 4. So you should use L by 4 square. Then you get here, this is ml square by 12 plus ml square by 16. If you add these two, it will be 3 plus 4, 7 ml square by 48 is the LCM. Understood, Neil, that example?
Yes, sir. Understood. Understood.
Okay. Now let's go to the one another body. If you have a uniform ring, if I have a uniform ring. So if you have a uniform ring, let's suppose I have a uniform ring, and the axis I am taking this axis. That is the axis here is perpendicular to the plane of the ring and going through the center of mass. So here I can say that about an axis, first I am taking about an axis about an axis passing through center of the ring, passing through center of the ring, and perpendicular to its plane. That means that if ring I have drawn in xy plane, then the axis is z axis. If total mass is m, you can take, let's take the radius as r. You can take a small element here. Let's suppose small element is a dm only. So dm and distance is r. So here di is going to be dm into r square. Now r is constant here. So if you integrate I, it becomes here only integration of dm because r square is constant. And you can integrate it to complete mass, that is m only. So you get here I is equal to capital M into r square. That is the moment of inertia of a ring about any axis that is passing through its center and perpendicular to its plane. Okay.
Okay, sir. Okay.
Now in the same page, you see the question number 45. Same page, you see question number 45. It says that calculate the moment of inertia of a ring about a tangent to the circle of the ring normal to its plane. So now in this example, you have a ring here and the tangent you have to draw not in the plane. Okay, tangent is perpendicular to the plane. So tangent is here like this. Here I have drawn. So this is going into the screen. And I have to find moment of inertia about this axis. I have to find. So first I know I'll take the center of mass here. This is the center of mass. And I know the moment of inertia about this axis. Now I'll take this and this, both are parallel lines, both are going into the screen. So and the distance between them is r only. So I am going to use the formula parallel axis theorem, that will be ICM plus m, and the distance is r square only. ICM itself I have found as mr square. So this is basically mr square plus mr square. So I should be equal to 2mr square. That should be the answer. Okay.
Okay, sir.
Now this is the table that you can see. This table, every derivation cannot be done, but you have to remember also many formulas for moment of inertia. Okay.
Okay.
Few important formula I am writing that you should remember.
Okay, sir.
Okay. Only few important one. There are a lot of bodies, but that is not given here. Whom they ask question frequently, that you should remember. Ring, I have told. Now it may be disc, circular disc. If you have a circular disc, and the axis is again perpendicular to the plane. About this axis, if they say what is I, then you should remember this I is m r square by 2. If I take a disk here and the axis is its diameter, it can be like this or it can be like this. Any diameter it can have. That means about this diameters, moment of inertia is half of this, is mr. If this is here x-axis and this I take as y-axis, so ix mr square by 4, or iy also mr square by, that means any diameter if you are taking, it is going to be mr square by 4, and the axis that is not in the plane of the disk, that is mr square by. Then you should remember about hollow sphere. This all I am telling you, that axis that is passing through center of mass. If you know about the axis that is passing through center of mass, then you can find the moment of inertia about any other axis using parallel axis theorem. So if you have a hollow sphere, if you have a hollow sphere, so hollow sphere is a three-dimensional body. So it doesn't matter here that what you have taken, what axis you have taken. If any axis that is passing through center of mass, it will be, if any axis that is passing through center of mass, it will be same formula. That means, just a minute, I can take here an axis that is this axis, or we can take this axis, or we can take this axis. Here all axis that passes through center of mass, moment of inertia is going to be 2 by 3 mr square. 2 by 3 mr square. If you have a solid sphere, if you have a solid sphere, let's take a solid sphere. Here also any axis you can take, this axis, this axis, or this axis. It should pass through center of mass just. Then moment of inertia is becoming 2 by 5 mr square. Hollow sphere, solid sphere, then they ask cylinder also. So one is hollow cylinder. If we have a hollow cylinder, so let's suppose I have a cylinder here. This is the axis. The radius is r, and the mass is m. So here I is equal to mr square. Remember that hollow cylinder is equivalent to ring also. And if you have, if
Sir?
you have a solid cylinder, so you should write that chart that is given. That chart you should write somewhere and remember it. It's very important. Okay.
Okay.
If you have a solid cylinder, then it is solid cylinder. So in that
Okay.
case, it is like a disk. So you can use mr square by 2. That is disk. Yesterday you had 4-hour classes.
Yes, sir. Yes, sir. I had it in the evening.
What they taught?
Sir, basically it was from Akash only. They had taken for physics and chemistry and all.
Okay, physics. What is going on? What taught? What last class you got taught?
Physics, they've actually just started this system of particles and rotational motion.
Okay, okay, okay.
And
So
test is on Sunday.
how they can complete it?
I don't know, sir. They've just started a week.
So I think they will take again then 4 hour, 3 hour more lecture, but that is not useful. One day, how much you will do?
Yes, sir. It won't even complete the chapter. The chapter is very long, I think. More than
Might
50
be,
pages.
Or might be they change the, but they cannot. Paper is not set by them, na. Paper is set by that Delhi only.
Ah, yes.
So Wednesday is normally week off, na there.
No, sir, it changes every time. So the last 2 weeks they haven't even holiday only.
Okay. Hmm. So moment of inertia concept you understood.
Yes, yes, understood.
So now let's discuss the concept of moment, that is we call as torque. It is given here, torque and angular momentum. Fine. Before that is angular acceleration that we have discussed, angular velocity that all we have discussed. Also cross product of vectors. Okay. You have this idea about vector product of two vectors.
Yes, sir, vector they have got.
Okay, fine. The vector products of two vectors, you know. Good.
Hmm.
So this is basically A vector dot B vector is equals to A B sine theta, right?
Yes, yes,
Where the theta is the angle between A vector and B vector. And if A vector is given as AX I cap plus AY J cap plus AZ K cap, and B vector is BX I cap plus BYJ cap plus BZK cap. Then you can also write as A cross B in matrices form, that says first you can write here I cap, J cap, K cap, AX, AY, AZ, BX, BY, BZ. I think this all you know. Am I correct?
yes, sir, yes.
Okay. So now let's do about torque. Okay. The vector, first we'll discuss torque and angular momentum. So first let's discuss about torque. Torque is basically called as moment of force. Torque is moment of a force. So moment of a force depends upon two things. It first depends upon how much force you are applying, and second it also distance that where you are applying the force, that is distance from the axis of rotation. Distance from the axis. Two things you have to take. So the torque is basically we write as the distance from the axis, and we always take the perpendicular distance r cross f, or we can write here is r f, that is vector product of r and f, r f sine theta, and n cap will be the perpendicular that you can draw. For example, let's suppose if I say this is the axis of rotation. If I say this is the axis of rotation, and at some distance r, at a point here, you are applying force F. You are applying force F. And the angle between the R, this is R here, the angle between R and F, let's suppose I take as theta. So you can definitely take two components of force. One component you can take as F cos theta, and one component you can take as F sin theta, F cos theta and F sin theta. So as I have taken R into F sin theta, so you don't take that component which is along the R. You take that component which is perpendicular to R, that is F sin theta. This will not produce any torque. This will produce torque. That means torque, if you try to write, you can take R multiplied by F sine theta. That means I can say distance from the axis, distance from the axis, and perpendicular component, perpendicular component of force. That is the meaning of torque. You got it, Neil?
Yes, got it, sir. Just
I
one
can,
second.
yeah, sure, yeah, sure.
Yes, sir.
You can also write in this way that torque is R sine theta into F. Both are same thing. I can, here I have written here this way, R into F sine theta. That I have taken perpendicular component of force and I have multiplied with R. I can also take perpendicular component of R and then I can multiply with F. For that, if let's suppose this was the R here that you can see, this is the R, and you have applied some force here, F. So what you do, and the angle is given as theta. So what do you do? Oh, you don't take the component of F. F, I'll just extend in backward here little bit. And then I'll draw the component of R. I'll draw a perpendicular on the direction of the force. So this angle will be also theta. This is also R sine theta. So F I have taken, F I have kept intact only as it is. I have taken component of R and then I'll multiply with. It means that to find the torque, you have two options, Neil. Either you take that component of force which is perpendicular to R, and then you multiply. Or you can take that component of R which is perpendicular to F and then multiply. That means take perpendicular component of one of two vectors out of R and F and then multiply with other. That is the torque. Understood? नील समझ में आ गया ये दोनों दोनों फार्मूला?
हाँ सर, समझ में आया ना।
ठीक, गुड। अब आप देखो एक एग्जांपल, ट्राई योरसेल्फ, पेज नंबर 26 आपके ये में, पेज नंबर 26, क्वेश्चन नंबर 25, 26 दो क्वेश्चन है।
ओके सर।
ओके, 25, क्वेश्चन नंबर 25 में, if force, that force is given as I cap minus 2j cap plus 3k cap is acting on a particle lying at the origin. ओके, ये बॉडी ओरिजिन पे ही है, ओरिजिन पे है, और ओरिजिन के अबाउट ही टॉर्क पूछा जा रहा है आपसे। मतलब डिस्टेंस कुछ है ही नहीं, यहीं पे आपने फोर्स लगा दिया। तो आर जीरो हो गया। अब आर अगर जीरो हो जाएगा तो टॉर्क का फॉर्मूला क्या होता है, आर एफ आर क्रॉस एफ। तो आर ही जीरो है तो नेट टॉर्क भी क्या हो जाएगा, जीरो हो जाएगा। ठीक है।
ओके सर।
क्वेश्चन नंबर 26 में लेकिन आर कुछ दिया हुआ है, देखो उसमें फोर्स वेक्टर दिया हुआ है आई कैप -2 j कैप +3 k कैप, और पोजीशन वेक्टर मतलब कुछ डिस्टेंस पे आर भी दिया हुआ है। आर कितना दिया हुआ है ये 3 i कैप +2 j कैप +k कैप। तो अगर हम यहाँ पे चाहें तो टॉर्क निकाल सकते हैं बाय द फॉर्मूला, दैट इज आर क्रॉस एफ, और फिर हमें क्या बताना है, जे कॉम्पोनेंट ऑफ द टॉर्क, जे कॉम्पोनेंट ऑफ द टॉर्क बताना है। उसके लिए टॉर्क आपको पूरा लिखना पड़ेगा। तो टॉर्क हम ऐसे लिख सकते हैं, आई कैप j कैप k कैप। आर में फर्स्ट 3 है, ये 2 है और ये 1 है, तो यहाँ लिख सकते हैं 3, यहाँ पे 2, यहाँ पे 1। एफ में है 1 - 2 3, 1 - 2 और आप इसको कर सकते। तो आई कैप के साथ इन दोनों को मल्टीप्लाई करना पड़ेगा, 2 × 3 6, और 1 × -2 -2, सो 6 -2, ये हो गया आई कैप के साथ। जे कैप के साथ आप यहाँ 3 3 को मल्टीप्लाई करो, 3 3 हो गया 9, और 1 1 1 प्लस के कैप के साथ ये 3 × -2, दैट इज -6, 1 × 2 2। So it means that torque vector is 6 minus minus plus 8 I cap, 9 minus 1 8 minus 8 j cap, and this is -6 -2 is -8 k cap. So they are asking only j component. J component here is -8. So my answer is -8 in this problem. Understood?
Yes, sir. Understood.
Okay.
One second. One second.
Yeah, yeah.
Yes, sir. Done.
Okay. After that, in your booklet is given about angular momentum.
Okay.
Angular momentum. So angular momentum is again moment of the momentum. It is moment of linear momentum. जैसे आपने ऊपर निकाला था मोमेंट ऑफ फोर्स, तो हो गया टॉर्क। अब आप निकालो मोमेंट ऑफ लीनियर मोमेंटम, इसको हम एल से लिखते हैं। और मोमेंट निकालने का मतलब कुछ नहीं है, आर से क्रॉस कर दो, आर क्रॉस लीनियर मोमेंटम को आप पी भी लिख सकते हो, आर क्रॉस पी। दैट मीन्स दिस विल बी अगेन आर पी साइन थीटा एंड एन कैप ऑल्सो यू कैन राइट। सो इसको आप ऐसे भी समझ सकते हो, आप पी का वो कंपोनेंट ले लो जो आर के परपेंडिकुलर हो, या आप आर का वो कंपोनेंट ले लो जो पी के परपेंडिकुलर, दोनों एक ही बात है। पी का मतलब लीनियर मोमेंटम जिसको आप एम भी बोलते हो, मास इनटू वेलोसिटी, जो अगर आप ऐसे लिखते हो तो ये बन जाता है एम वी आर साइन थीटा, L equals to mvr sin theta, or in vector form also we can write it is m तो कौन स्केलर है, बाहर रखो इसको, r वेक्टर क्रॉस b वेक्टर, तो ये आपका एंगुलर मोमेंटम समझ में आ गया।
यस सर। यस सर, डन।
ओके, इसमें एक हाँ एक रिलेशन देखो, जैसे रिलेशन बिटवीन टॉर्क एंड एंगुलर मोमेंटम, एंगुलर रिलेशन बिटवीन टॉर्क एंड एंगुलर मोमेंटम। तो जैसे सेकेंड लॉ क्या कहता है, सेकेंड लॉ ऑफ न्यूटन, इट सेज दैट फोर्स इज इक्वल टू रेट ऑफ चेंज ऑफ लीनियर मोमेंटम। वैसे ही आप बोल सकते हो एंगुलर मोमेंटम इज इक्वल टू, सॉरी, वैसे ही हम बोल सकते हैं टॉर्क इज इक्वल टू rate of change of angular momentum, dl by dt. That means you should remember that it is called second law of Newton in rotational motion. So torque is equal to rate of change, rate of change in angular momentum, rate of change in angular. You can also write that torque is equal to final momentum, final angular momentum minus initial angular momentum, और कितना टाइम लगा उसमें, टाइम टेकन, दैट फॉर्मूला आल्सो वी कैन यूज। ओके, अंडरस्टूड।
यस सर, अंडरस्टूड।
सो यू कैन सी क्वेश्चन नंबर 27, try yourself, this is page number, how much page is number not given, 28. A particle of mass 1 kg is moving about a circle of radius 1 meter with a speed of 1 meter. Calculate the angular momentum of the particle. So a particle is moving in a circle, okay, and its mass is given 1 kg, mass is given as 1 kg, radius is given 1 meter, and the speed is also 1 meter. The speed is also 1 meter per second, and it angle between V and R is 90 degree. So L formula is always mvr sin theta. M is given 1, V is given 1, R is given 1, and sin 90 is also 1. So final answer is 1. And mass is, unit is kg, velocity is meter, and here also 1 meter, so meter square per second. So answer is 1 kilogram meter square per second. आया समझ में ये क्वेश्चन?
यस सर, जस्ट वन सेकंड।
यस यस।
Yes, sir. Done.
Okay.
Yes.
Now 29 and 30, please you try in 2 minutes. If not, then I'll solve.
Okay.
29 and 30.
Sir. Done.
Okay, you got the answer?
Got the answer.
Okay. Tell me 29 answer.
29 का answer is 10 kg meter square per second.
Okay, and 30 answer.
2 nm Newton.
Yeah, that's correct. Okay. Now let's discuss equilibrium of a body. Equilibrium of a body. Now, a body should be in equilibrium or complete equilibrium. For that, it should be in both type of equilibrium, that is translational equilibrium, translational equilibrium. For that, net force acting on the body should be zero. Net force acting on the body should be zero. And that, and it should be also in rotational equilibrium. rotational equilibrium. And for rotational equilibrium, net torque acting on the body should be zero. And if both conditions are there, then only the body will be in complete equilibrium. Understood?
Understood.
Like if you see sometimes translational equilibrium is there, but rotational is not there. If I'll take a rod and that rod, let's suppose, is fixed here, it cannot move. It is fixed here. At this point, I have fixed it. So, and I am applying a force here, F. Do you think it will move? It will not move because the rod is fixed. Am I correct?
Yes, yes,
So it will not move. It will not translate. So it is in translational equilibrium. There is no doubt about it. It is in translational equilibrium. But due to this force, a torque will act. Torque is, let's suppose this distance I'll write as L. And this angle is 90 degree. So you can see that here a torque is acting about this fixed point F into L. And due to this torque, it will move, it will rotate. So it is not in rotational equilibrium, only translational equilibrium, only translational equilibrium. It is not in rotational equilibrium, not in rotational equilibrium. Equilibrium. Understood?
understood.
Similarly, if this rod is there and the rod is fixed here, I have fixed this rod and I am applying a force F here, and here I'm applying the force F like this. So you see that I have applied two forces and both forces are opposite to each other. So again, it is in translational equilibrium because forces will cancel each other. It is translational equilibrium. Translational equilibrium. But it is again not in rotational equilibrium because both will produce torque in the same sense. This will try to, rotate the rod in this direction. That is clockwise torque. This is also clockwise torque. And this is pulling down. If the distance is L, it is also pulling down. This direction is also clockwise. So both torque is clockwise only. So it is not in rotational equilibrium. We can find the torque net. Net torque I can find here. This is F into L because angle is 90 degree only. And here also F into L. So I have to add the torque. That will be 2 into F into L. Understood, Neil?
Understood.
But if I say I have a rod that is fixed here and I have one force F and here one force F. Now forces are in same direction, that will be balanced by the support here, whatever force it will apply. But you can see that this F torque is now, if this is L, this F is trying to rotate in clockwise direction. But this F is pulling upward, that means this will try to draw in anti-clockwise direction. So this torque is here clockwise and this torque is here anti-clockwise. So now they are in opposite. So if you try to find the net torque acting on the body, then if I take one torque clockwise is positive, anti-clockwise will be negative. So they will cancel. That means net torque is zero. So here the body is in equilibrium because force is also, net force is also zero and net torque is also zero. Understood?
Understood, sir.
You just revise the notes, and then we can discuss the principle of moments another in the next class. Okay, tomorrow. Okay.
Okay, okay, sir. Okay.
Okay, bye.
Thank you, sir.